So hi again, everybody. In this video, we essentially introduced the computation of transport barriers in 3D flows. So in the last video, we concluded our discussion on the transport barriers in 2D flows with the computation of the active barriers from a turbulence simulation. And in this video, we start with the 3D transport barriers. So to the structure of the 3D folder, it's essentially the same as in a 2D case. So you have here one folder dedicated to the data, another folder dedicated to the demos, which will essentially be the folder we will be looking into extensively, and then one folder with all the subfunctions. So inside here, you can basically find subfunctions which you use for computing particle trajectories, so for integrating. The first notebook simply integrates a trajectory given an initial condition over some finite time interval. And this notebook here simply computes the velocity field at some arbitrary points in space and time. Then, of course, you also have additional utility functions, which I like to call them. These are simply functions like, computing doing the eigenvalues, computing the range of the flow map, finding local maxima in the velocity from a scalar field, computing the vorticity. So this is all pretty basic stuff, I would say. So back to our 3D folder. The data folder contains two data sets essentially. For the moment, I might be adding more in the coming weeks or months, but for the moment, it just contains two data sets. One data set is a turbulence data set. So this data set is essentially, we will be using this data set when we will be dealing with the active barriers in 3D. And the data, so I've extracted, actually I've put here already a MUD file which contains some snapshots of the Laplacian of the velocity field. If you want to have access to this data set and want to download maybe other versions or other portions of this data set is originally from the John Hopkins turbulence data set. So it's made available from the John Hopkins turbulence database. And so you can simply click on this and download the data set. I warn you that this data set is pretty big, so it might take some time to download. I've given all the instructions here, so we will actually be going through these instructions once we're dealing with the active barriers. And that's pretty much it for the turbulent channel flow. Now, the other data set is a pretty standard one. It's the ABC flow. So the ABC flow is essentially a solution to the Navier-Stokes equation, an analytic solution to the Navier-Stokes equation. And it's actually, so the steady ABC flow is actually a solution to the Euler equation. So without the viscous term. Now, there are two versions of the ABC flow which I uploaded. One is the steady one and one is the unsteady. Now, since these MUD files are essentially too big, especially this ABC unsteady MUD file is way too big to be stored on GitHub, I've created this little script, ABC, which briefly introduces the ABC flow. And so as you can see, you have here first the steady ABC flow, which is essentially it's an analytic flow, a periodic flow, basically, also on a periodic domain. And one can also define its viscous counterpart, which is the same thing essentially with a decaying, so with an exponential decaying term, where nu simply is the viscosity. And of course, one can do all these computations with the analytic velocity field. In fact, that's even desired for numerical accuracy. However, since we want to simulate a setting where the velocity field is given from experiments or from direct numerical simulation, we'll proceed by discretizing this velocity field first, and we will discretize it according to the following spatial resolution and the following temporal resolution over a time interval from 0 to 20. Now, of course, the time interval only matters in the unsteady case, because in a steady case, we will not need to store snapshots so velocity snapshots at different time intervals, but just at one time interval, basically. So I recommend, or actually I want you to run the script, which again should be very quick. So this first set here simply computes the MUD file for the steady BC flow. So essentially here we will have the velocity field U, V, and W on a grid domain. And the second MUD file simply does the same for the unsteady velocity version. Now here you of course need to store this extra dimension, which is time, which you did not need to do in the steady case. However, essentially the two things are basically the same. The reason why we use this velocity field is that it has been used in lots of papers, also within our group, so that you can compare things. We hence recommend that you also maybe start with this 3D velocity field. Now back to our original folder. Now we will check out what's inside this demos. Inside this demos, there are basically various subfolders. So one folder is simply called the decomposition. What this folder does, it simply does the dynamic polar decomposition, the polar decomposition, and the single level decomposition from data. So these are simply scripts which do this decomposition from data. For example, here's the SVD, which simply does the single level decomposition on the gradient of the flow map. Very straightforward. We will not go through this exactly, since since we will first need to cover the gradient of the flow map computation. So now back to our original. So back to our demos folder. Then we have, of course, a subfolder, or actually a folder on the advective barriers. So this folder essentially contains tools that we are already aware of, essentially. So we're computing the FTLE, the LAVD, the TRA, and various other diagnostics on 3D datasets. Then one folder is dedicated to the active barriers. So he will be essentially running the FTLE and all these other diagnostics, not on the original velocity field, but on the active barrier equation. So basically on the viscous part of the Navier-Stokes equation. Now, in this first video on the 3D datasets, we'll be focusing especially in this introduction folder. And we will start with the computation of the velocity field. So we'll illustrate how to compute. So it's very simple stuff. We'll illustrate simply how to compute and use the notebooks to evaluate the velocity field at arbitrary points in space and time on a three-dimensional steady or unsteady velocity dataset. So we'll be dealing here with the unsteady VC flow. Hence, we need to first import this data for the unsteady VC flow. Then, of course, we need to define a bunch of computational parameters, which we always do. These computational parameters simply include so the number of cores you want to use for the parallel computation, whether the flow has periodic or non-periodic boundary conditions. So since the ABC flow has periodic boundary conditions, you would need to set all these parameters to true. Keep in mind that in case the data set you're dealing with does not have periodic boundary conditions, but for example has a wall, then you would need to set these appropriate conditions to false. So you need to basically have the velocity on the wall to be 0 if you assume no slip boundary conditions, and then of course you need to set the periodic domains to small. Then you need to specify whether the velocity field is steady or unsteady. Now, you would need to, so the velocity field is unsteady, which we're dealing with because we're dealing with the unsteady VC flow. Now, if we were to deal with the steady VC flow, then we would need to set this parameter to false. This array simply contains the domain where the velocity is defined, which of course will be 1 everywhere. So because the velocity field is defined everywhere, then we just simply compute the mesh of the data set and the spacing between two points on the mesh grid. Next thing we need to do then is we need to interpolate the velocity from this discrete grid data. This is essentially done here. Now you need to first import the interpolant. Since the flow is unsteady, you need to import the interpolant for the unsteady case. If it was steady, then you would simply need to do interpolant steady. That's pretty much it. The important thing to consider here is that computations in 3D are pretty time involving. So what we'll be doing is we will use linear interpolation both in space and time. One needs to be a bit careful because if you use linear interpolation both in space and time, and you want to compute derivatives, then of course one needs to be careful that you do not The one needs to be very careful with the computation here. If you have a linear interpolant in the velocity field, and then you compute spatial or time derivatives. So of course, the interpolation here is linear. This is essentially done to make sure that there are no non-values in the array. So every time there's basically a non-value, I will set this to 0. And then we compute the interpolant here, where this is simply a list, where the first element in a list is simply interpolant for the u, so for the x component of the velocity field. This is for the y component, and this is for the z component of the velocity field. And then we can simply compute the velocity field by doing what? Well, let me run this script actually. So if you want, let's say, to compute the velocity field at time equals 3, on this, at this point, where again, the first dimension here, so the first axis indicates the x, this is the y, and this is the z. And let's forget this for the moment. So let's forget this for the moment. And you want to compute the velocity at this point here. Sorry, at this point here, then you simply need to, of course, first import the velocity function and then pass this t and x to the velocity, to this velocity function. So this is simply 3 in our case, and this is simply this array here. X, Y, Z are simply the mesh grid of the data. This one here is simply the 3 interpolants. This variable here indicates whether the domain is periodic or non-periodic, and this variable here whether it's steady or unsteady. So if I run this now, then you can see that, okay, the velocity is, if I can print this, is essentially this, this quantity here, and the shape of the velocity array that you get is the following. Now one can, of course, also evaluate the velocity at multiple points at multiple points in the space at the same time instant. So to do that, I can, for example, define this mesh grid here. So I want to compute the velocity field over this mesh grid, which I defined here. And to do that, I simply need to define x the following way, where this is simply, so this x is simply a free so this x now here is simply 3 times 1 million array, 1 million. Why? Because I've got like 100 times 100 times 100. And of course I can, if I now plug this into the velocity field, then the velocity also needs to have the shape of 3 times 1 million. Okay. So that's important to keep in mind. That would be pretty much it for the video. In the next video, we will compute trajectories, and then we'll slowly move forward to then computing the transport barriers from 3-dimensional data, velocity data.